Okay, so picking up where we left off from video 3, remember that we just phrased our extra assumption, which is the assumption we're making for conditional proof. And it's being added to the hypotheses that were given in advance for the entire theorem. Right? But the extra assumption is now being phrased in the following form. It's f prime of p is of full rank. Namely, its rank is exactly k, which we can also think of as the smaller between k and d. Those are the two dimensions of that matrix, f prime of p. All right. Well, how that's going to help us with the implicit function theorem is as follows. Before I even write that, let's just recall from an earlier point in, I think it was in the fall, we proved this, that if a matrix has rank R, then it has R linearly independent columns. But there's no set of R plus 1 linearly independent columns. Okay, and similarly for the rows. Meaning the matrix has exactly R linearly independent rows, but there's no set of R plus 1 or more linearly independent rows. So those are facts about rank, the rank of a matrix, that we know from very early on in the course. Okay, we're going to apply that to this situation to say that the matrix f prime of p must have k linearly independent columns, because k is its rank. Now, we don't know which k columns are linearly independent, but it really doesn't matter. The proof is the same. It's just a minor modification, like regardless of which k of those d columns happen to be the independent ones. Let's remember that the matrix f prime of p, which I also called A earlier, is of size k by d. So it has k rows and d columns, where k is at most d. So k out of the d columns are linearly independent, and no more. Right? There's no set of k plus 1 or more columns that are linearly independent. Okay? Because that's simply what the rank means, part of what the rank means. The rank equaling k implies this. All right, now we don't know which k of the columns those are, but we know there are k of them, and it really makes no difference which k they are, because we would just do the same reasoning in any event. So I'm going to suppose, just for simplicity's sake, for ease of notation, that it happens to be the first k columns that are linearly independent. Okay? It doesn't have to be the first k. It could be the last k columns, or it could be any selection of k out of the d columns. The only thing that's going to affect is that what I'm basically going to do is I'm going to subdivide the coordinates of the point x into two groups, which are going to be the y's and the z's, right? Now, when you do that, the y's are going to correspond to those columns that are the linearly independent ones. So let me just draw you a kind of schematic diagram here. We have a k by d matrix, and k of the columns are independent, but they can skip around a little. There can be gaps. Maybe these red ones are your linearly independent columns. But the ones that are skipped, let me do in blue, those are not part of it. Okay. So what I would do then is I would label, I should also point out that each column corresponds to a variable. This matrix is not just any old matrix, it's a derivative. It's the derivative of f at the point p. And if you think about what that looks like, this would be df1 dx1 at p down to dfk dx1 at p. Then you'll have df1 dx2 at p down to dfk dx2 at p. So you see the pattern is that this first column here corresponds to the variable x1, because you're partially differentiating all the component functions, f1, f2, up to fk. By the way, that column is the function f itself. The function f by itself, these are separate, just has those component functions. But you see that f1 just generates the first row this component function f1 generates this entire first row. f2 will generate the next row. fk generates the bottom row. But the variables, like x1 here, corresponds to this first column. x2 would correspond to that second column. So the columns correspond to variables. That's why there are d of them. So the variables are like x1, x2, x3, all the way up to xd. But what I'm going to do is subdivide those variables. If these are the linearly independent columns, and there are k of them, as we know, since the rank of A is k, we have these k linearly independent columns. So I'm going to call those y1, and then y2, and then y3, all the way up to y sub k. So only the red ones. And notice that I'm labeling them as y's, y1, y2, y3, from left to right, but skipping over those blue ones. So I have y1, and then I skip over all the blue ones and jump right to y2. And then I skip over here and I jump right to y4, and so on and so on. Now the blue ones are going to be labeled as z1, z2, and so on, z3, okay, all the way up to zd minus k. So you see, that's how it could look in general. And in that case, what I would do is I would write the point x not as y concatenated with z, because concatenation means that you list all the y's first, and then you list all the z's. Right, that's what y concatenated with z would look like. And that's not what x is going to look like in this picture. Rather, what x looks like in this picture is like x1 is the same as y1, but x2 is z1. So you can see it here. Like this x1 is the same as y1, but x2 is the same as z1. x3 is the same as z2. But then x4 is y2. And so on. So there's some interlacing. That's the point, is that the y's are interlaced with the z's in some particular interlacing order. That interlacing order is completely determined once and for all by which k of these d columns are the linearly independent ones, which is totally determined by the nature of this matrix. In fact, if you row reduce it to reduced row echelon form, then you can read off which are the linearly independent columns, because they'll be the ones with the leading ones in them. Like column 1 will have a leading one, let's say. Column 4 will have a leading one. Column 5 will have a leading one. You take all the columns with the leading ones in them, and that tells you which k. So anyway, the point is that there's a particular interlacing order. The y variables and the z variables have to be interlaced in a particular order that's totally determined by the shape of this reduced row echelon form, which you can determine kind of once and for all. Okay, but within their respective sequences, notice that they're labeled in increasing order. Like this is y1, y2 is next, y3 is after that. Okay, sorry, I'm touching that dead spot again. Okay, and then within the z sequence, again, the order is fixed. Within the z sequence, you have z1 first, and then z2. It's just the manner in which those two sequences are interlaced together that has to be determined by just looking at which k of the d columns are the independent ones. Okay? So what I'm saying is, x may not be exactly the concatenation of y and z, but instead x is going to be some sort of pseudo concatenation, which we can write like this, where you have the variables y and you have the variable z. They're just not exactly concatenated. Rather, they're interlaced in a particular order. And the interlacing order is known. It's not some mysterious unknown thing. It's a known interlacing order. So we can write that this way if we please. But just to avoid that notation and to avoid any complication, although the proof would work perfectly fine with a general interlacing order, but I'm going to assume, for the sake of simple notation, that it happens to be the first k columns. I'm just going to assume that it so happens to be the first k columns. This is unlikely to happen in practice, but in the context of this proof, we may as well. There's no loss of generality in assuming that it's the first k of the variables that are the y's, and then the last d minus k are the z's. So in other words, x1 is the same as y1, x2 is y2, xk is yk, and then xk plus 1 is z1, so on. Okay, let's assume this, just for ease of notation. And then we can write x as exactly the concatenation of y and z, with no interlacing necessary. Right? Now, remember, it's the red ones that are linearly independent. But that's exactly that k by k block that we called the partial Jacobian of f with respect to the y variables at the special point P. And remember that the special point P is also being subdivided. It has d coordinates, but we can subdivide. We can call the first k of its coordinates a, and the last d minus k of them b. So that's just writing P in this way as a concatenation. Now, by the way, if we had used this, which is like an interlaced concatenation, and that's an ambiguous notation because there are many, many different interlacings. So to disambiguate that notation, you have to specify the interlacing order in advance. But of course, the nature of this reduced row echelon form specifies that interlacing order for you, just once and for all. So there's no ambiguity. We have a given interlacing order, and we can form these interlaced concatenations. Okay, so if we were working with that general situation, we would also be writing P as an interlaced concatenation of A and B. But we're just not bothering doing that. By making this assumption, just for the sake of notational ease, we're just assuming that the interlacing order is the simplest possible one, just so that we don't have to worry about all these different notations. Okay, anyway, so that k by k block is that partial Jacobian at the point P, in other words, at the point A concatenated with B. The other block, this k by d minus k block, this is a k by k block here. Yeah, that other block is also a partial Jacobian. What was it? It was the partial Jacobian of f with respect to the z variables, evaluated also at the point P, or at the concatenation. Now, what do I know about this? What do I know about this? Well, I know that these are exactly the linearly independent columns. These were exactly the k linearly independent columns of the matrix A. So I have a square matrix with linearly independent columns. What does that tell me? The fact that its columns are independent tells me that its rank is full. Its rank is as big as it can be, which is exactly the minimum of its two dimensions. Now, it's a square matrix, so both of its dimensions are k. So that means the rank is exactly k. It's full. It has full rank. But remember back from our study of linear algebra that, so I'll just remind you, that a square matrix of full rank is necessarily invertible. In fact, this was part of what I called the fundamental theorem of linear algebra. Remember what that looked like? Is like it said, let A be square. Then the following are equivalent. And it gave a number of equivalent conditions. A is invertible. A is at full rank. The reduced row echelon form of A is the identity matrix. What else? Columns are independent. The rows are independent. Determinant is non-zero. Null space is trivial. Column space is the full space, whatever the size of the matrix is. So on and so on. By the way, then A transpose will also be invertible. Okay, here's how you know that. A and A transpose have exactly the same rank, and they're both square. If A is square, then certainly A transpose is square. And remember that as a general matter, as a general theorem, the rank of A transpose is the same as the rank of A. So they're both square, they have the same exact rank, and if A is of full rank, then of course A transpose must be of full rank. But that also tells you that A transpose is invertible. So you see there's a number of ways, and now we're going to have another way also, which is that the Gramian. Since A is of full rank, then the Gramian is going to be invertible as well. Okay, when you take a linear algebra class, you're going to see there's many, many, many conditions that can be added to this list. All equivalent conditions to being an invertible matrix. Okay, this applies, of course, only to a square matrix here. Anyway, so that was part of it. A square matrix is of full rank if and only if it's invertible. These are, in fact, equivalent to each other. So if we go back here, we see we have this k by k block. It's a square matrix, and we know that it's of full rank because its columns are independent. All k of its columns are linearly independent. So therefore, it must be an invertible matrix. So we can conclude that this matrix here is invertible. And that is exactly the non-degeneracy condition that we needed to be able to solve locally for the y variables as a function of the z variables, as an implicit function. That was exactly what the implicit function theorem required. So you see, we can now apply the implicit function theorem, and the conclusion is going to be that there exist these neighborhoods, a neighborhood of A, which is an open subset of K space, that A belongs to, of course. Yeah, the notation, when I write this, n sub A, that notation implies that A is in it, and that it's open in its respective space. Okay, and also there exists like a neighborhood of B, which is open subset of D minus K space, and there exists an implicit function, psi, from one of those neighborhoods to the other, which is C1, excuse me. Okay, such that for all y in this neighborhood, and for all z in this one, the equation f of y z equals 0 is true if and only if y is psi of z. Okay? So here's what we're going to get from that. I claim that if I take my constraint set S and intersect it with the Cartesian product of those two neighborhoods, which, let's recall, is open. This is an open subset of the Cartesian product of those two spaces, which is simply D space again. If this was an exercise that you had on a problem set from a long time ago, the Cartesian product of two open sets is open. Okay, so each of these neighborhoods is open in its respective space, so the Cartesian product is some open subset of D space. And remember, S is sitting in D space as well. It's actually inside W, which is inside D space. So it's appropriate to take that intersection. Okay? Also notice that that intersection is non-empty because the point P belongs to it. Let me discuss why that's true. Remember that P certainly belongs to S by hypothesis, because in fact P represents like the global maximum point of F restricted to S. So P has to certainly be in the domain of that function, which is S. But also, A is in this neighborhood, B is in this one, and therefore the concatenation of the two, which is exactly P, belongs to the Cartesian product. After all, that's what a Cartesian product is. Right? This Cartesian product is just the set of all concatenations yz, where y is in the first neighborhood and z is in the second. So yeah, P is certainly in that set as well. So P is in S, and P is in this neighborhood, this Cartesian product. So it's also in the intersection. P belongs to this intersection. So therefore, this intersection is not the empty set. All right, but the claim that I want to make is that this intersection is actually exactly the range of the function phi, where I'm going to define the function phi in this way. It's a function of z, and its definition is that you take psi of z, which was the implicit function, and you concatenate that with z. And it's on the domain n sub b. Let me just be a little more detailed about that. Its domain is n sub b, which remember is an open neighborhood of d minus k space. So I'm just defining this function right now, this function phi of z. You just take that implicit function, psi of z, which we got in the last step here, that exists. We know that that's a C1 function. And we're just going to take that function, take its value at z. Oh, what's the size of that? That's a vector that, sorry, I did something slightly wrong here. Let me correct a mistake. Yeah, psi is a function of z, and z belongs to this neighborhood. So I wrote the mapping a little bit backwards. It's actually mapping NB to NA. I'm glad I caught that. Oops. Yeah, so it's mapping NB into NA. Yeah, I think that probably in the last video, part 3, when I mentioned the implicit function theorem, I messed that up too at that point. So just, if you were a little confused at that point when I said that, just realize now that, okay, it's really should be this way. That's the direction, because psi is going to be a function of z, and it's going to equal y. Right? That's what this equation right here says. So z is the thing that's that's near the point B, and that's in d minus k space. Y is the thing that's near A. That's in k space. Because we're solving for k of the variables in terms of the remaining d minus k. Good. All right. So anyway, if I take that's how many variables does that account for? Well, the values of psi are in this space here. Psi maps into this, and this is a subset of k space. So you see the psi has k components. But then I'm concatenating that with z itself, which has an additional d minus k components, because z is a point in d minus k space. So altogether, here's what this looks like. Oh, and then the whole result I'm calling phi of z. It's still a function of z, obviously, since all of its components are functions of z. But yeah, in detail, it looks like this. It's going to have like psi1 of z. And actually, I'll even maybe do it in slightly more detail. All the way up to psi k of all the z variables. And then the last few components are just the z variables themselves. So you see that how many components are there in total? Let's count them. This is the first component of phi. You can call it phi 1. This would be the kth component of phi. This is the k plus 1th component of phi. And notice it's a function of z. It only involves the z1 coordinate of z, and it's constant with respect to, say, z2 and z3. But that's okay. It's still a function of the whole vector z. And then you keep going, and what's this last one? This last one is going to be like phi sub d of z. I don't have quite enough room to write it there. Let me squeeze it in up here. This last one is going to be phi sub d of the vector z. So you see that phi maps into d space. It's got k component functions plus an additional d minus k. So in total, d components. So this phi, where can I write this? This function phi that I've defined right here has this domain in d minus k space, and it maps into d space. So its domain is this open subset of d minus k space, and it goes into d space, and by the way, it's also C1. How do I know it's C1? All right, well, we knew that psi was C1, right? The function psi is known to be C1 just as part of the implicit function theorem. Okay? And so all these first few component functions here are smooth, or C1, just for that reason. And what about these remaining component functions? Well, those are obviously smooth. Z1 is obviously a smooth function of the vector z. It's a projection function. It's like the projection of the vector z onto the first axis. Then z2 is the projection of the vector z onto the second axis. Well, projection functions are, in fact, infinitely differentiable, so they're certainly C1. So yeah, this function here is also a C1 function. Good. And therefore, we can talk about the derivative of phi at some point z. And that's going to be a matrix of size d by d minus k. So you have to read it this way. D by d minus k. And specifically, we can plug in the point b. And that's going to be a specific matrix. Z is a variable point somewhere in this neighborhood. But I can plug in the specific point b, which is certainly in that neighborhood. And that's going to give me like a specific matrix with numerical entries of size d by d minus k. That matrix is going to have great importance in what's to come. So let me put a box around that. Okay, great. Now, I still have this claim back here. I made this claim we have to establish. This intersection is also equal to the range of that function phi. What that tells us in words, before I prove the claim, let me just sort of explain the meaning. Okay, the meaning of it is that the function phi provides a one-to-one, smooth, and non-degenerate, I'll explain the meaning of each of these terms in turn as we come to them, parametrization of the patch S intersected with this open set, which is a patch of S itself. Okay, so let me explain. The set S may be some very large set, extended far in space. It's the constraint set. But we have a particular point on it, namely the point P. Let me just draw kind of a schematic picture. We have this constraint set sitting in space, and there's a specific point P on it. Okay, now, we have a certain neighborhood of P. It's this open neighborhood of P, which I'll just draw as if it's like a box. And it's neighborhood of A, where A is going to be like one projection, crossed with a neighborhood of B, where B is like some other projection. Okay? And so if we look at the intersection of S with that box, so yeah, this box is like open in D space, which is what's pictured here. But S is going to have some sort of intersection with that box, which is what I'm calling a patch of S. It's not the full set S. It's just a small patch of S around the point P. So it's like a local patch of the constraint set just around P. Now it's that local patch that's parametrized by the function phi. See, the function phi is going to take some portion of a lower dimensional space, namely d minus k space, some neighborhood or open set in in D minus k space, which is n sub b. B is a specific point in there. And the function phi comes along and just maps that open set in D minus k space right onto that patch, kind of in a one-to-one, non-degenerate fashion, smoothly. Okay, let's try to understand all those terms. And so yeah, in other words, we have a parameterization. Parameterization just means that if I track the movement of this point, then I can also track the movement of a corresponding point on this patch. So, for example, if I take this green point and let it move horizontally, then I can track which way this blue point is going to be moving on that patch. Or if I let this green point move vertically, for instance, then I can track, which way this blue point is going to be moving on that patch. So let's say like a horizontal movement of this green point within this neighborhood corresponds to movement along some curve here. And then let's say like a vertical movement of that green point within that neighborhood corresponds to this curve, something like that. So yeah, I have like a set of parameters. Or what are my parameters? Well, the parameters are just the coordinates of this space. If the original coordinates of D space are called x's, x1, x2, etc., up to xd, these parameters are called z's. This is like z1 up through zd minus k. In terms of those parameters, I can track. So yeah, these parameters are completely independent, right? The z1 through zd minus k are independent. You can let them vary independently of each other. But then by plugging those into the function phi, remember this function phi is exactly a function of z, then you get something that moves around on that blue patch. And here's the thing, not only does it move around on that blue patch, but it completely covers that blue patch. That's really what the claim is saying. The blue patch is exactly this set. It's the intersection of the constraint set S with that neighborhood. That's the blue patch in my picture. Well, not only does the point phi of z move around on that patch as z moves in its neighborhood, but in fact, phi of z completely covers that blue patch, because that blue patch is exactly the range of the function phi. So every single point on that blue patch is the value of phi of z for some z. So the phi of z's are, yeah, the image of this point z as it moves around under the mapping phi totally covers every single point on that blue patch. Okay? And that's really what the claim is saying. So we have a good parameterization, not of the full set S, but of a local portion of S around the point, surrounding the point P. All right, that's what I want to prove. And now it's quite easy to prove that claim. Okay, the idea goes like this. We're going to look at the intersection, and we'll just like work on it step by step. Okay, first let's express it this way. It's the set of all points x that are in S and also in this Cartesian product. So we can write that as like all concatenations yz, because that's how we broke down x, where first of all, that point, to be in S at all, to be like to meet the requirement of being in S, it first of all has to be in W. And what else had to happen? The constraint equation had to be true. Remember that this breaks down into these two conditions. But let's also recall that our constraint equation has been rewritten in the form big F equals 0. Okay, so I don't have to write it in the form that we're used to, this form here. I can rewrite it in this completely equivalent form, and I'll do that. Okay, and then also the fact that x is in that Cartesian product just means that y has to belong to this neighborhood, and z has to belong to this other neighborhood, because that's the meaning of this Cartesian product here. X is this concatenation. So to be in that Cartesian product, y just has to be in that first set, n sub a, and then z has to be in that second set, n sub b. Okay. All right, now I'm going to say the following thing. First of all, I claim that we can delete this condition here. This is unnecessary, but it's not quite so simple. I don't know how to spell unnecessary, sorry. Okay, not quite that simple, but I'll explain right now. So here's the idea. Remember, W is an open set. Let's recall that W is the intersection of capital U and capital V, both of which are open. So finite intersection of open sets is open. And then also, the point P is inside it. So P is in W, and W is open. Okay. That means that there's a ball around P that's fully in W. Like there's some ball around P, right, which is fully in the set W, where the radius is positive. Now within that ball, we can basically shrink these two neighborhoods if necessary, so that that Cartesian product ends up being within that ball. And therefore also within W. Okay, but we have to shrink both of these neighborhoods if needed. See, we're free to do that, because once we have two neighborhoods that work, we can always reduce them in size, as long as we keep the point A inside n sub A, and keep the point B inside n sub B. Take your neighborhood that you have that contains A and just like make it smaller, but keep A inside, like make sure it still contains the point A. Right? The implicit function theorem will still apply. Because if you remember back to the proof of the implicit function theorem, there was a kind of minimum size that worked, but we could use any smaller size we liked. Once you meet the minimum size requirement, you could always make the size of that box. We use these boxes, if you recall, but you could always make the size of those boxes smaller, and the same reasoning would hold. So there's no loss of generality if we shrink those two sets small enough so that their Cartesian product fits within that ball. Okay, because remember that the point P is inside both. Point P is inside this one as well. So you're just shrinking it around the point P. You can imagine like closing those down around P, so small, so tightly around P that it fits within this ball, centered at P. And then it will belong to W anyway. So you see, the fact that the point X is already in here, the point X is already in this set, well, if that set is already contained within W, then that point is also in W automatically. Just the fact that X belongs to that Cartesian product already implies that X belongs to W. Once we arrange that that Cartesian product sits within W, which we always can arrange by shrinking these neighborhoods if necessary. And so then we don't have to write that condition anymore once that arrangement has been made. So it's like without loss of generality. Okay, then we can delete that unnecessary condition. And just copy all the other ones. All right, but now notice also that these are exactly the locality conditions in the implicit function theorem. And that tells us that this last condition can be replaced, since the locality conditions hold. The equation big F equals 0 can be replaced by the locally equivalent equation y equals psi of z. And that's going to turn the set into the set of all points yz, such that y is in this neighborhood, z is in this neighborhood, and y is exactly psi of z. Okay, but once we know that y is psi of z, I can replace y in the concatenation with psi of z. And then just say that z is restricted to this neighborhood. See, that's the same thing, because all I'm doing is using this equation to replace y here with something equal to it, namely psi of z. And then we don't need any independent information about y. Oh, actually, we should check that. We should check that. If I replace y with psi of z, do I know that this condition is going to hold? And therefore, can I just ignore? I don't have to write it because it's automatic? Answer is yes, it is automatic. Because coming back to the implicit function theorem, remember that psi of anything is automatically in n sub a. Psi of anything at all is going to map into n sub a. So, since y is equal to psi of something, psi of z, that y is indeed going to automatically be in n sub a. So we don't have to even write that condition, it's just automatic. And so this is enough information. Okay? Anyway, but then also let's remember that this concatenation here is precisely what we defined as phi of z. So the set becomes all things of the form phi of z such that z is in n sub b. In other words, all vectors phi of z where z is in the domain of phi, because that's what n sub b is. And that's just the range of phi. Okay? The set of all values phi of z where z runs through the domain of phi is exactly the range. So we started this calculation with this set, which was that local patch of S around P, surrounding the point P, and we ended with this description. So we've proven our claim. Okay, good. So that gives us that parameterization, and it's a smooth parameterization. Oh, yeah, I forgot to take you through. Remember I said that it was one-to-one and smooth and non-degenerate. So let me just explain. Smooth is obvious. This just means it's a C1 function on its entire domain. And we know that. We said that here. All right. We all know what a one-to-one function is, but I haven't proven that it is a one-to-one. It's very easy to prove. let's just take a moment to show that this really is a one-to-one function. The way you prove a function is one-to-one is you show that if I set the values equal at 2 points, then that's supposed to imply that the 2 input points are equal. So we need to show that the equation phi of z equals phi of w implies that z must equal w. So 2 distinct input points would always have to lead to 2 distinct output points. You can't have 2 equal outputs unless you have 2 equal inputs. That's the idea of a one-to-one function. All right, well, it's easy. It sort of answers itself. You see, this is nothing but psi of z concatenated with z, and the other one would be psi of w concatenated with w. But if those two are assumed to be equal, then if you just chop off these coordinates and chop off these corresponding coordinates, the coordinates left have to equal the coordinates left. So yes, indeed, z must equal w. So you see what I'm saying is if I have like one long list of coordinates here, there are d of them, and then I have another long list of coordinates, there are d of those, and I know that those two lists are equal, coordinate by coordinate. So if you simply delete the first k coordinates in each list, then the remaining d minus k coordinates of each list must also be equal, one by one. So yes, that tells us that z must equal w. So yeah, it is a one-to-one function. It's a smooth function. And then what we mean by non-degenerate is that its derivative at any point z in the domain has full rank. Okay. Now let's ask ourselves, what does full rank mean in this case? What is the maximum possible rank? So we know the size. It's d by d minus k. And so the rank of this matrix, phi prime of b, is at most the minimum of d and d minus k. And of course that's just d minus k. Since k is non-negative, d minus k is less than or equal to d. So that would be the maximal possible. So being a full rank just means that the rank is exactly equal to d minus k. Now this I have not proven yet. This is as yet unproven. But I just wanted to explain what I meant when I said that the parameterization is non-degenerate. It means that the derivative matrix at every point in the domain is of full rank. It's maybe not so obvious why that's important. But I can tell you roughly why it's important. If we look back at this picture, see, a matrix of full rank if you look at its corresponding linear map. All right, I'm leaving a few important things out here, but roughly speaking, here's our parameterization, phi of z. That also has a derivative, let's say at b itself. That's a linear map. It's really a matrix, but every matrix corresponds to a linear map. So if I look at that derivative, specifically at this point b, it's just some constant matrix. Let me call that matrix M for matrix. It's like some specific matrix of size d by d minus k. But that has a corresponding linear map, L sub m. And that's going to map vectors in d minus k space to vectors in d space. Okay, it's going to take a vector such as this horizontal one, and it's going to map it to a vector like this. Okay, well, first of all, notice that there's this point phi of z, which is the corresponding point to z itself. If I have this point z here in the domain, phi of z is some point on that patch. Okay. This horizontal vector, let's say, right here, just for an example, is going to map under this linear map to a tangent vector. It's going to be tangent to the set S. You're going to have to take that for granted right now, because I haven't really even explained what I mean by a vector being tangent to a set. That's a technical term that I haven't defined yet. We're going to do that later. But just take on faith for now. I'll explain and rigorize this later. But that's what's going to happen. And then, for example, also, this red vector, let's say this vertical one here, is going to map to some other tangent vector. Okay? Now, what we don't want to have happen is that two linearly independent vectors in the domain, such as the green one and the red one. I have this green horizontal vector, and I have this red vertical vector in the domain. What I don't want is for two linearly independent vectors to map to two linearly dependent vectors. Because that would be as if a two-dimensional space is being folded into a line. I want a two-dimensional domain space to map onto a two-dimensional codomain space, so that the parameterization is not collapsing my set. You see, this patch should resemble this domain very closely. The only thing that's different between them, really, is that this domain is flat. It's sitting inside of a flat space. It's d minus k dimensional flat piece. It's a piece of flat space. When you embed that into d space, when you take that flat piece of d minus k space and embed that into d space, it's being warped. It's being sort of distorted or bent in the shape of the set S. So that patch of S is not flat. It's sort of curved. But other than that, the two sets should really resemble each other very, very closely in shape. Because, the mapping phi is it's a nice mapping. It's 1-to-1. It's smooth. In other words, C1. But I also would like it not to collapse my set n sub b. Squish it into a lower dimension. You can imagine taking a flat piece of paper, cut out a shape, cut out some nice shape, like a kidney bean shape, and then you want to bend that. If your piece of paper was flexible, made of rubber, you can imagine bending that around some surface. But what you don't want to have happen is that you squish it up into a piece of string. You can imagine taking a little sheet of rubber, cutting out a kidney bean shape, and you can stretch that onto some curved surface. But what you don't want to do is squish it up into a little string, a one-dimensional thing. So I want the dimensionality of my domain here to be preserved. And that means that independent directions in the domain, two independent directions in the domain, such as this one and this one, should always map to two independent tangent directions. Now, to get that to happen, I need this linear map to be of full rank. Because linear maps of full rank preserve dimension. They preserve linear independence. A mapping of, when you have a matrix of full rank, the corresponding linear mapping always takes linearly independent vectors and maps them onto linearly independent vectors. So that's the reason why a parameterization, it's not good enough for a parameterization to be 1-to-1 and smooth. We also want it to be non-degenerate, so that it doesn't collapse dimensions. It takes a d minus k dimensional flat patch and curves it to become this local patch of S, but it doesn't squish it up into a lower dimension. It never takes independent directions and maps them to the same direction. So that's the idea. We can call that a good parameterization. So this claim, together with our verification of 1-to-1ness, which we did here, and together with the smoothness, which we already verified. Okay. So the three properties together say that this phi is a good parameterization of our patch. Okay, and that's really the intuitive meaning of the claim, this claim here. Okay, great. So now what do we do? All right, well, now the rest of the proof is pretty straightforward linear algebra. Really pretty stuff. Okay, so let's do it. All right, the first thing to notice is that if we now restrict the point x to the set S and to the neighborhood NA cross NB of the point P in S. So in other words, back to our picture, I'm restricting the point x to be on this patch. So it's on the set S, but it's also within this neighborhood. The intersection of those two is that patch, the blue patch. So if we now restrict x to that patch, that means that x is in this intersection. In other words, it's in the range of phi. So we can write x in the form phi of z for some z in this domain. Okay? But then what about f restricted to S at the point x? Well, that's the same as f of x, obviously. Remember that x is in the set S, so these two agree. Okay? And then x itself is phi of z, as we just said right here. So you see that now we can bring the chain rule into play, because we've written the quantity of interest as the value of a composition at a certain point. Okay, so what I'm going to do now is I'm just going to use the chain rule. All right, now why am I allowed to use the chain rule? Well, we know something. We're given that this value is less than or equal to this value, because P is given to be a global max. Right? P is given to be a global maximum point for the function f restricted to S. So this inequality is clear. And it holds for all x. It holds for all x in the relevant set. Now let me be very, very precise about it. It holds for all x in S intersected with that Cartesian product. Okay, but then by writing the left-hand side of that inequality in this way, like this is the left-hand side of that inequality, and also in a very similar way, we can write the right-hand side. Okay, so by plugging in b basically here for z, then p gets plugged in for x. Let's verify that. Notice that phi of b, by definition, is psi of b concatenated with b. But what about psi of b? Well, let's also remember that y is psi of z is locally equivalent to this equation, provided we have the locality conditions. Meaning that, y is close enough to a, and z is close enough to b. All right, well, if I take z to equal b, then the question is what goes here? Well, we can answer it by looking at this other condition. If z is equal to b, the question is what y value satisfies this equation? And the answer is obvious. It's a, because that's just f of p. P is the concatenation of a and b. And f of p really is 0. That's like the special solution point. So that's going to tell us that a is the right value there. And notice that, of course, the locality conditions are definitely satisfied. If I take z to equal b, b is certainly in this neighborhood. And if I take y to equal a is certainly in that neighborhood. So the locality conditions do hold, and therefore this is a valid equivalence. So we can identify this as simply a. And then we know that that concatenation is just p. So therefore our inequality, which is this, which holds for all x in our local patch, can be written equivalently as f composed with phi of of z is less than or equal to f composed with psi of b for all z in this neighborhood. Okay, so this one was given. That's the thing that expresses that p is a global maximum point for f restricted to s. But now we've put that in an equivalent form that involves compositions. And what it says, this simply says, oh, what do I mean by this? Yeah, f composed with phi at z is less than or equal to f composed with phi at b for all z in this neighborhood of b. Okay. What this says is that b is a local maximum point for the composition f composed with phi. It's a local maximum because there's an open neighborhood of it where it is the maximum in that open neighborhood. And the openness is very important. The fact that n sub b is an open neighborhood of b is in that neighborhood, and that neighborhood is open in its space. Because remember, that's how local maximum is defined, is that like around that point b, there's at least a ball, where on that ball it's the maximum. Now this n sub b is not necessarily a ball, but it has a ball in it. Right? N sub b is some open set containing b, and because it is open, there is at least a ball of some positive radius within that. And of course, if the function is maximized at b for this whole set, then it's certainly maximized at b for this smaller subset. So it is indeed a local maximum. Now, that's really good, because we know a great theorem about local maxima. When you have an unconstrained maximum, and it's a local maximum, meaning that it's a max on an open set, then we know that the gradient has to be 0 at that point. Right? So by prior theorem, the gradient of this function at that point b must be 0. That's key. All right, let's see how to use that. By the way, we can also take transposes. If we transpose both sides, then we can call it the derivative matrix of this at the point b. But then we'd have to write this as a 0 row. It's going to be 1 by something. It's a row matrix. Okay, let's figure out the something. First of all, I want to point out that this composition is still scalar valued, because f is scalar valued. And f is the outermost function. So that's what gives the composition its values, ultimately. But the domain of it is going to be the same as the domain of phi, which is n sub b, and that's in d minus k space. And that's going into the reals. Okay, and it's also C1, because it's a composition of two C1 functions. We know that this is C1, and we also know that f is C1 by hypothesis. That was one of the global hypotheses that we were given at the very beginning of the theorem. The chain rule theorem tells us that the composition of two C1 functions is another C1 function. Okay, anyway, so the derivative matrix is 1 by d minus k. And it's only when you transpose the derivative. So the derivative is like a row matrix. Size 1 by d minus k. Oh, why is it d minus k? It's because like you're going from one space. You're going from d minus k space to one space. So you have to read it backwards. When you transpose that row matrix to get a column, meaning a vector, that's what we call the gradient. So, in general, the gradient of f is the Jacobian derivative transposed. So we can take this theorem and sort of transpose it and get that. All right, good. Now we can use the chain rule to simplify the derivative in this equation here. The chain rule tells us that you can write the derivative as like f prime of the inner function and then phi prime of b. Now remember, phi of b is just p. And then this is the matrix I called M, back in this picture. So let me continue to use the name M for that matrix. Oh, how do I know that phi of b is equal to p? Okay, I think we proved that here somewhere. Yeah. Phi of b is equal to p. So we can make that replacement. All right, and now our equation becomes f prime of p times the matrix M equals this zero matrix of this size. And we can transpose it. And when you take transpose of a product, you have to reverse the order. Let's just recall that general rule of transposes. So we're going to get M transpose times f prime of p transpose equals the zero matrix of size d minus k by 1. Now that's a column matrix. D minus k rows, but only one column, so that's a column matrix. We can write that as a zero vector. And then this is the gradient of f at p, by the way we define the gradient. Okay. And let me also introduce a short name for M transpose. I don't really want to keep carrying around that transpose sign. So let me just introduce, I don't know, capital R. So that's going to be a matrix of size, what is it? Let's go back. This M was of this size, d by d minus k. D by d minus k. So the transpose will be d minus k by d. Right, let me call that matrix R, so this matrix here. So fine, we have this equation now. R times the gradient of f at p, which is a vector, equals the zero vector. And this R is some specific matrix. It was phi prime of b transpose. And we know its size is d minus k by d. Great. Now think what this equation says. This equation says that the gradient of f at the point P is in the null space of R, because R nullifies it. When you left multiply by R, you get the zero vector. So another way to say this condition, another way to say this conclusion, is that the gradient of f at the point P belongs to the null space of the matrix R. Good. Now, before we go any further, let's just try to determine the dimensionality, the dimension of that null space. The dimension of the null space of a matrix is what we call the nullity of the matrix. The nullity of R. That's just a definition of the word nullity. And let's recall the rank nullity theorem. We proved this theorem in class quite some time ago. But here's the idea. The rank of a matrix plus the nullity of the matrix is always equal to the number of columns of that matrix. All right, so if we apply the rank nullity theorem to our situation, we can write the nullity of R as its rank. As the number of columns. How many columns did R have? I think it was D. Let's just check. Yeah. Has D minus K rows and D columns. Okay, so the number of columns of the matrix, which is D, minus the rank of that matrix. Now I want to figure out what the rank of that matrix is right now, so that we can complete this calculation. So let's take a look at that. I claim that the rank is exactly D minus K. But going from here to here, we have to see why. And then the answer is going to be just K. The nullity is going to be K. So this space right here is the vector space. It's, by the way, a subspace of D space. Because, this vector here is d-dimensional, and it belongs to that set. So if it's a subspace of anything, it has to be a subspace of D space, since it contains d-dimensional vectors. So yeah, it's a subspace. We know that the null space of a matrix is a vector space. The only question is what space is it a subspace of, but it clearly has to be a subspace of D space, since it contains a d-dimensional vector. And it can't contain vectors of different dimensions, like mixed dimensions. So if it contains even one d-dimensional vector, then it must be a d-dimensional, like it's sitting in d-dimensional space. But it has its own dimension. It's a subspace of its own dimension. And that dimension turns out to be k by this calculation. So basically this gradient vector, by the way, the reason it's d-dimensional is simply because it has these d partial derivatives in it. So it clearly has d coordinates. All right, anyway, so that gradient vector, which is some vector in D space, but it doesn't just belong to D space. It belongs to a particular k-dimensional subspace of D space. And that's going to turn out to be very important. All right, but we still need to calculate the rank of the matrix R and show that it comes out to D minus k. So let's work on that now. All right, remember R is the matrix phi prime of B transpose. So let's look at what phi prime actually looks like in general. Actually, even before that, phi of z itself, remember, has these components, like psi 1 up to psi k, and then z1 to zd minus k. It's always useful to write that because to generate the derivative, the Jacobian derivative, all you have to do is take each component and write down its partials. So like here we'll have psi 1 prime of z, which is a row matrix, consisting of the partials of psi 1. Then we'll have a row psi k prime of z, which will consist of all the partials of psi k. All right, then in this row we're going to have all the partials of z1 with respect to the z's. Well, we know what those are. 1, 0, 0, 0. Then in the row after that we're going to have all the partials of z2 with respect to the z's, which look like this. Okay, and then in the bottom row we're going to have all the partials of zd minus k with respect to the z's, which look like that. But let's just make sure that we get the number of columns correct. Like, we know that this is going to be d minus k rows, because they just correspond to these d minus k rows. But how do I know I get the number of columns right? I claim it's also d minus k columns. Okay, that's easy. Just look at the map phi. It goes from a subspace of d minus k space into d space. So when you read the size of its derivative, you read it backwards. D by d minus k. So we know that this matrix has to have d rows in total, and then d minus k columns. But here I have a block, which is d minus k by d minus k block. And notice that it's not just any old block, it's exactly the identity matrix, because it has 1s on the diagonal and 0s everywhere else. So it's exactly the identity matrix of size d minus k by d minus k. Okay, well now you can see what the rank of that matrix is. It has these rows, all of these rows here, are linearly independent from each other. And how many rows are there like that? Well, there's d minus k of them. So you see this matrix here has at least d minus k independent rows. So in other words, the rank of it is at least d minus k. But on the other hand, its rank is at most d minus k also. See, its rank is at most the smaller of its two dimensions, which is also d minus k. So on the one hand, it has rank at least d minus k. On the other hand, it has rank at most d minus k. So therefore, its rank is exactly d minus k. That's this matrix here. But R is just the transpose of that. And a matrix and its transpose have the same rank, always. So that proves that R has indeed a rank of precisely d minus k. That validates this calculation. It shows that this null space here, the null space of R, is a subspace of D space, which has dimension precisely k. And we know that the gradient of f at the point P is an element of that space. Good. So our next step is going to be to find a basis of that space. We're going to find a basis for this null space. All right. Here's how it goes. First of all, notice that if I take any point x in this intersection, we know that's also the range of phi. Whoops. So therefore, x is going to be phi of z for some z in the domain of phi. But what do I know about g of x? We know that any such x has a g value equal to c, because that's a precondition for being in S in the first place. This point x is in S in particular. It's actually in both of these. But yeah, in particular, it belongs to S. That's the constraint set. And this equation is involved in, belonging to the constraint set. So this is because x belongs to the constraint set. So if I replace x with this expression, then what it will tell me is that g of phi, oops, this phi should have an arrowhead, g of phi of z must equal c identically for all z in that neighborhood. See, okay, yeah, I did this like slightly a little bit wrong. I started with the x in this patch and said that x is equal to phi of z for some z. But the thing is, I can reverse the reasoning. I could say for any z, for any arbitrary z in this neighborhood, if I define x as phi of z, then that x ends up being in that patch. Okay, that x, in other words, ends up being in S intersect this neighborhood. Because after all, this is nothing but the range of phi. Since x is defined as phi of something, it's certainly in that range. And in particular, it's in S. So therefore, in particular, g of x must equal c. And therefore, g of phi of z must equal c. But you see that it's now true for any arbitrary z. For every single arbitrary point z in that neighborhood, we end up with the same conclusion, this equation. So in fact, it's an identity. That's why I'm using the triple bar. It's identically true. It holds identically for all z in this whole neighborhood. Right. The reason I'm emphasizing that is because when two functions are identically equal, notice that this function here happens to be a constant function. It's just a constant function of z, whose value is always equal to c. But anyway, when two functions of z are identically equal throughout an entire neighborhood, then you can differentiate both of them, as long as they're both differentiable, and set their derivatives equal identically. Okay? And they are indeed both differentiable, because we know that phi is c1, and we know that g is c1 by hypothesis. That was one of the givens in the original statement of the theorem. So the chain rule theorem tells us that the composition is also a differentiable function. And of course, a constant function is always differentiable. So because those two functions are identically equal throughout an open neighborhood, throughout an open set, their derivatives must be identically equal throughout that same open set. So we can conclude from this that the derivative g prime of phi of z times phi prime of z, that's just by the chain rule, gives the derivative of this composition. Right, but that must identically equal the derivative of a constant function, which is 0, identically for all z in that same neighborhood. Now, what is the size of that 0 matrix? It's not hard to determine. Just by thinking about that constant function. That constant function was mapping z to c. And z is a point of dimensionality d minus k, and c is k-dimensional constant. So you read the derivative this way. It's k by d minus k. That's what that 0 matrix is. Okay, good. So now I'm going to plug in z equals b, which is certainly in this neighborhood, so it's a valid choice for z. And that's going to give me g prime of phi of b times phi prime of b equals 0. Okay, I'll transpose. And that's going to give me r. Okay, sorry, this matrix was m. And then m transpose is called r. And then I'll have like g prime of p transpose. Remember that this is just the point p, as we proved a while ago. Yeah, and that's going to equal another 0 matrix, but it's transposed, so it looks like that. Good. Now, what I'm going to do next is I'm just going to take this matrix here and break it down column by column. So let's just remind ourselves of the equation we have. R times g prime of p transpose equals this 0 matrix. I don't even remember the size. Okay, like that. Oh, that's very easy to break down column by column. They're just all 0 vectors, the columns. Sorry, let me be a little more careful notationally. I've always done this with columns. I've always drawn these lines. So I'll just continue doing that now. All right, it's d minus k by k, so there are k columns here. And each of these 0 vectors belongs to d minus k space. What about on this side? I have the r out there. What are the columns of g prime of p? All right, well, if you look at g prime of p by itself, the rows of that, the first row is g1 prime of p, where g1 is the first component function. The second row would be g2 prime of p, where g2 is the second component function, and then you'll have gk prime. Okay? But if I take the transpose of all that, which is what I have here precisely, those become columns. It's like g1 prime of p transpose, g2 prime of p transpose. And those are just gradients. This first thing is like the gradient of g1 at p. then the gradient of G2 at P, and then the gradient of GK at P. All right, and then let's also remember from an earlier point in the semester that when you have a matrix subdivided into blocks that are horizontally laid out this way, and you have another factor, matrix factor, that's sitting to the left, that other matrix factor that's on the left can actually be distributed into each of those blocks. That's one of the block multiplication rules. So I'm going to take that R and just distribute that into every column. And what that's going to give me is a matrix whose first column is R times the gradient of G1 at P, whose second column is R times the gradient of G2 at P, whose kth column is R times the gradient of GK at P. And that is going to equal a matrix whose columns are all 0 vectors. So we can take that apart. We can equate the first column of this side with the first column of this side. Equate the second column here with the second column here. And equate the last column here with the last column here. And that gives us all these conditions. R times this gradient is the 0 vector. R times all these gradients. Right, but that means that the matrix R nullifies all those gradients. In other words, all of those gradients, every one of those gradients belong to the null space of R. So, and remember, that's a subspace of D space of dimension exactly k, as we already proved. So I have a list of k vectors in a k-dimensional space. Aha, that sounds very promising. Maybe these form a basis for that k-dimensional space, because there are the correct number of them. There are k of them to span a k-dimensional space. But of course, there's one thing missing, which is we need to know that they're linearly independent. So that's the question now, is are these gradients all linearly independent? Because if they are, then they will be a basis. Right? They're linearly independent, they will turn out to be, and of course there's the correct number of them, so they span a k-dimensional space. The spanning is automatic, by the way. How do I know that? Let me just take a moment to, just informally. If I know that my space, let's say I have a subspace of something, and I know its dimension, and I know I have a list of vectors in there, and it's the correct number of vectors, k of them, all in that space, and I know that they're linearly independent. Suppose all that is known. Then I claim that, in fact, those vectors automatically span that space. So it's a linearly independent spanning set. In other words, it's a basis. Okay, but how do I know they span? Well, you can always take any linearly independent set and augment it to a basis. Augment it meaning by adding vectors. Augment it, if necessary, by some additional vectors in V to get a basis of V. Remember, we proved in general that any linearly independent set in a vector space can be augmented to become a basis for that vector space. But now you see what the rest of the argument is, that if I had to augment it by adding anything to it, then the dimension would be wrong. Because you'd have A1 through AK, and then let's say you've added B1 through BL. But these are all now linearly independent, and they span. So the span of these vectors is now V, and they're all independent. So what's the dimension of V? Would be K plus L, which is strictly bigger than K. That contradicts this. So you'd have a contradiction. So no augmentation can be necessary. Therefore, the original set must have spanned V to begin with. Okay, so yeah, we just need to come back here and prove that all these gradients are linearly independent, because there's the correct number of them, k, to span a k-dimensional space. We already know that this space is k-dimensional. All right, good. Well, how do I know that they're linearly independent? Okay, that's going to be easy. Remember, we know that the matrix G prime of P is of full rank by our extra assumption. That's the matrix I think I called A earlier, meaning its rank is k. But means it's sorry, let me just write down what that matrix looks like. What this matrix looks like in terms of its rows, the first row would be G1 prime of P. Second row would be G2 prime of P as a row matrix. And then GK prime of P. The reason these are row matrices is because G1 is scalar valued. And the Jacobian derivative of a scalar valued function is a row matrix. Anyway, you see that there are k of them. And so because the rank is exactly k, that means all k rows are linearly independent. When the rank is k, it means we have k linearly independent rows. But there are only k rows. Right? The matrix is of size k by d. So, in fact, all k rows turn out to be linearly independent. by the fact that the rank is k. Remember, rank k means that you have k linearly independent columns, and you have k linearly independent rows. But there are only k rows to begin with. So in fact, all the rows are linearly independent. Right? And then now when you transpose, when I take the transpose, those just become gradients. All right, but remember that the rank of the transpose is the same as the rank of the original. Also k. And there's only k columns. So for the same reasoning, all k columns are independent. Linearly independent. And that's exactly what we wanted. So what we've now established is that these gradients here, the gradients of the component functions g1 through gk, evaluated at the point P, form a basis for this null space. Okay, by the way, I keep saying this null space. That's the tangent space. It's going to turn out, we're going to look at this in a future video. That null space is the tangent space. Remember I drew that picture, like the set S, and then there's this point P. Well, there's a tangent space. It's like if S is a surface, then that tangent space would be a tangent plane, which just grazes past that surface, touching it at the point P. That's what that null space turns out to be. But why that is, we'll have to await a future video. Okay? For now, we're just thinking of it as some k-dimensional subspace of D space, with no particular geometric significance. But I want you to know that it really does have a very, very important geometric significance. Namely, it's just the tangent space. Okay. Well, okay. It's the tangent space translated so that it passes through P. Because, you know, a space passes through 0. But if you translate it so that it passes through P, that's what it becomes. All right, well, where are we now? We previously proved that the gradient of f at the point P belongs to that null space. And we now know that that null space is exactly the span of its basis, which is the list of gradients of g1, g2, through gk at the point P. Well, what does it mean to belong to the span of a bunch of vectors? It means that the gradient of f at P is exactly a linear combination. Of that basis. Okay? And so these for some coefficients in the reals. So in other words, there exists a vector lambda in k-space such that P and lambda together satisfy the Lagrange equation, which is this equation here. But in fact, it also satisfies the Lagrange system. Because what's the second equation in the Lagrange system? The second equation in the Lagrange system is simply the constraint equation, which we know is true, because P is in the set S, the constraint set. So you see, we have both conditions for the Lagrange system. That means P satisfies the Lagrange system, and that was precisely what we needed to prove. That was our burden of proof. Remember, the logic of the situation was we had all the givens, all our givens here. There were many of them. We made this extra assumption, for the sake of argument, that P fails to satisfy the degeneracy system. We then used that together with our givens. So we used all the given information together with this extra assumption to derive that P satisfies the Lagrange system. And the conclusion we draw is that if P fails the degeneracy system, then P satisfies the Lagrange system. In other words, by pure logic, either P satisfies degeneracy system, I should say, or P satisfies Lagrange system. Okay, and that's exactly the conclusion that we wanted. So you see where the subderivation ended here, and we jump to this step by appealing to conditional proof. Great. All right, so that concludes the proof of the Lagrange multiplier theorem. It's not an easy theorem to prove. It's quite difficult. And we're not even really quite done yet because I didn't prove that linear algebra theorem about the Gramian. We still have to investigate the Gramian. So I'm going to leave that to another video. So yeah, that'll be Lagrange multiplier video 5. And in it, we'll prove the Gramian stuff. And maybe I'll do another example. There was something else I wanted to do too. Oh, I want to talk about the tangent space, the significance, geometric significance of the tangent space. And I want to show you in particular that, remember, we described it as the null space of R, which was this matrix like that. So we described this tangent space, in other words, we're going to end up writing it this way. It's the tangent space at the point P of the set S. Okay, we described it in terms of a parameterization, a good parameterization. Phi. And now notice that phi does not parameterize the entire set S. It just parameterizes a local patch of S near P. And that's all that's necessary, because the tangent space is local to P. The only relevant stuff is not, like, the relevant piece of S is not the entire set S as a global object, but just the portion of S near P. The shape of that is what determines the tangent space at P. How it's shaped far away from P is completely irrelevant. So we don't need a parameterization of the whole set S globally. We just need a parameterization of a local patch. So it parameterizes a local patch of S near P, and that's all that matters. So yeah, we can express the tangent space, like we know now how to express the tangent space in terms of a good parameterization of some local patch of S. Namely, it's the null space of the derivative of that parameterization at the relevant point, transposed. Okay. When I say the relevant point, I mean B, because B is the parameter value. B is the parameter value that corresponds to P. In light of this equation. So yeah, you take the derivative of your good parameterization, phi prime, you plug in the relevant parameter value, B, and then take the transpose, and then take the null space. That's one way of describing the tangent space, but it turns out there's a much better description of it. Namely, it turns out that it's also equal to the column space of G prime of P, where G was that function that, the constraint equation comes from. But why these two are equal is going to be the subject of the next video, partly. So in the next video will just be a catch-all, where I'll take care of this issue. I'll sort of answer this question so that we can reveal the geometry of the tangent space a little better. Plus I'll do another example, and I'll talk about the gradient. Okay, and that'll conclude the theory of Lagrange multipliers. A lot of stuff here. A lot of really interesting stuff. Okay, but then we'll be ready to talk about integration in higher dimensions. Good. See you guys soon.